Starting, all attendees are in listen-only mode.
Hello, and welcome to the October Pacific Northwest DEWS Drought and Climate Outlook webinar. My name is Janelle Christensen, and I am with the USDA Northwest Climate Hub. This bi-monthly webinar series is hosted by NIDIS, the USDA Northwest Climate Hub, and Oregon Climate Change Research Institute. It is designed to provide partners and other interested parties in the Pacific Northwest with timely drought and climate information. Each webinar will be tailored to reflect recent, current, and forecasted conditions and climatic events, but will also include discussions of observed impacts and other relevant updates from across the region. Webinars and recordings and other supporting materials will be posted on drought.gov later this week. After today's webinar, you will have the opportunity to provide feedback that will help us improve this webinar series. So please take a moment and tell us what you think. Today's speakers include Joe Bloomgard-Zagrodnik with Versec Weather Solutions, John Gottschalk with NOAA Climate Prediction Center, Megan Collins and Ben Hatchett with Desert Research Institute, and Keith Jennings with Linger Technologies. We will be using the Q&A box at the right side of your screen for questions during the presentations, and we'll address those and additional questions during the Q&A period after the 4 presentations. Before we begin with the presentations, we wanted to highlight the partners who make this webinar series possible. The Northwest Climate Hub develops and delivers science-based region-specific technologies and practical information that will assist agricultural and natural resource managers with climate-informed decision-making in Idaho, Washington, Oregon, and Alaska. Visit the website listed to get more information. The Oregon Climate Change Research Institute is a network of dozens of researchers at Oregon's public universities that work closely with other public and private entities. OCRI is housed at Oregon State University. OCRI advances understanding of regional climate impacts and adaptation and cultivates climate-informed communities. NIDIS was established in 2006 by public law with a mission to improve the nation's capacity to proactively manage drought-related risks by providing those affected with the best available information and resources to assess the potential for drought and to better prepare for, mitigate, and respond to the effects of drought. NIDIS is building the foundation of a national drought early warning system through the development of regional DEWS, where networks of partners and stakeholders share information and actions that help communities cope with drought. While the ultimate goal is a national early warning system, we recognize that impacts and early warning information differ across the regions. Each DEWS has many of the same base ingredients, but ultimately have their own flavor to reflect the needs of their region. The Pacific Northwest DEWS was officially launched in February of 2016, and our strategic plan and information is current activities is available on drought.gov. To facilitate our early warning system, more precipitation observations are needed. We encourage you to join COCORAS, the Community Collaborative Rain, Hail, and Snow Network. This is a unique nonprofit, community-based network of volunteers of all ages and backgrounds working together to measure and map precipitation, which is rain, hail, and snow, as well as condition reporting. Observation by COCORAS observers and precipitation events and the lack of precipitation are important events to capture and improve our understanding of weather. To become a volunteer or learn more, visit cocoras.org or contact your state coordinator. The names and emails are going to be put in the chat box. The 17th annual Oregon-Washington Water Year Meeting, 2020 Recap and 2023 Outlook will be held as 2 virtual morning meetings on October 25th and 26th, tomorrow and the day after. The goal of this meeting is to share and gather information regarding climate impacts of the 2022 water year. Continuing drought in some areas, flooding in the fall of 2021, and the exceptionally wet spring will be the focus. This meeting will also offer the opportunity to learn from others about mitigation actions that were taken. Both days will include time for discussion and peer-to-peer learning, in addition to hearing from forecast experts on what to expect for 2023. The Idaho Water Supply Meeting will be held on November 9th, 2022, in person in Boise, Idaho, with an option to attend virtually. This annual meeting is held each year to recap the water supply from the previous water year and provide an outlook on climate and water supply for the coming water year. In the outlook portion of the meeting, the NRCS also provides an estimate of the runoff needed to meet water supply demand for the coming year. This needed runoff estimate sets the stage for drought risk in the coming year. These meetings are critical for identifying vulnerabilities and opportunities for increasing drought and climate resilience in the agricultural, power, and recreational sectors of Idaho's economy that are dependent on the state's water resources. There is no cost to attend either meeting, but you are required to register and see the links in the chat box. October marks the start of the 2023 water year. Now that the wet and dry swings of water year 2022 are complete, we want to hear from you. How was the Pacific Northwest impacted? We encourage you to fill out the Water Year Impact Survey. The goal of the survey is to gather information about impacts and response actions that were implemented during the 2022 water year, which is October 1st, 2021 through September 30th, 2022. Due to either abnormally dry or abnormally wet conditions, the survey should take about 15 minutes to complete, and your responses are vital for informing the water year meeting and the Pacific Northwest Water Year Impacts Assessment. Tribal nations contend with drought data gaps, such as the lack of monitoring on tribal lands, but nonetheless have shown their resilience to drought and have communicated the need for tools and resources to help management. In response to the needs expressed by tribal partners, NIDIS is pleased to announce a new map customization feature for tribal nations. Developed in collaboration with NOAA's National Centers for Environmental Information, this feature allows users to display reservation boundaries for more than 300 reservations across the US on any of the maps available on drought.gov. NIDIS and National Centers for Environmental Information launched the new Tribal Boundary Map feature in direct response to the NIDIS Tribal Drought Engagement Strategy, which NIDIS developed in close consultation with 22 tribal natural resource managers. Learn more using the link in the chat box. If you have any questions for our speakers that are not answered in today's Q&A, please feel free to reach out to them directly. Their contact information is in the chat box. Now, let me welcome Joe Boomgard-Zagradnik to discuss the climate recap and current conditions.
All right, okay, I think you all can, you see like my little, there we go, okay. Thanks. My name is Joe Boomgard-Zagradnik. I'm based in the Seattle area, so I'll be talking to you all about the regional climate conditions for the last few months. I actually kept this image here in the background. This was a storm exactly 1 year ago today that was much bigger than our current little storms, but we're starting to see some change in the seasons finally. So it's a little bit weird to talk about all this warm weather since it's now cloudy and rainy here, but you'll see that drought impacts don't get erased overnight. So anywho, so let's get into the plots here. So the last 30 days of temperature, we've seen near record warmth across much of the Pacific Northwest, and some of the greatest warm anomalies of as much as 9 degrees Fahrenheit in the southern Cascades of Washington, and large areas of 6 to 9 degree Fahrenheit average temperature anomalies over very large portions of Oregon, Washington, Idaho, Montana, and not much better to the south or east either. And this is average temperature. The high temperature anomalies are even greater than this. It's near record warmth across a large area thanks to the delayed onset of the rainy season, which shows up in this plot of last 30 days of precipitation anomalies, and many of those areas that were running 6 to 9 Fahrenheit above normal in temperature are have been running less than 25% of normal precipitation and less than 5% of normal in some of the mountainous areas that normally have seen a start to rainy season by mid-October. And there was, at the end of September, there was one event in Southwest Washington. So that's kind of one exception to the rule in the last 30 days. There was, I think, I saw there was 1.25 inches in Pullman, for instance, on September 29th or 30th. So there's a little bit of some positive anomalies there, but pretty much the large scale picture has been very dry to start autumn. And even going back now to the last kind of 90 days, July, August, and September, mean temperature was record warmth across much of the Pacific Northwest. And there is pretty much no exceptions to that rule. Everywhere was either record warmth or near record warmth across the region. So it was a pretty bleak picture ever since the switch kind of flipped in early July from a cold, rainy spring to a hot and dry summer, and it's stayed that way until the switch flipped again in the last week or so. And precipitation percentiles here, the record driest summer and early autumn was mostly confined to western Washington, west of the Cascade Crest. Other areas have been generally below normal, but not as bad as it was in western Washington, and even some positive anomalies in southeastern Idaho. But and there was a fairly, if you look at a bigger picture, there's a fairly strong monsoon this year across the Southwest. So there would be more positive anomalies elsewhere in the West, but western Washington in particular has been dry. Looking at why the kind of large scale reason for that, well, there's basically been ridging along the coast, along the west coast of North America. First on the left, July and August shows that persistent ridge centered right along the west coast of BC, and in September and October the pattern has only become more prominent. Pretty much the same story on repeat for quite a long time, and that's kind of the recipe for getting record warmth and dry, is to just be stuck in a ridging pattern like that. Perhaps a bit of better news is when we look at year-to-date plots, January through September, and when I was making these slides, I was comparing them to the ones I had from last year, and things actually look better on the year-to-date plots for 2022 than 2021. So, and that's thanks to the first half of the year. So we're running slightly above average temperature-wise for the year, which is nothing new in this era, but it could be worse. And precipitation, Southern Oregon is kind of where, and down into California is where the annual deficits are the worst. Southern Oregon, Southern Idaho, Washington's pretty much near normal, with even some positive anomalies in the southwest part of the state. The Drought Monitor, again, widespread drought conditions across, there's it everywhere in the Northwest, other than this tiny bit of far southwestern Oregon, have at least some, or at least some level of yellow. But with especially east of the mountains in Oregon is where we're seeing those D3 drought conditions. A lot, and then western Washington, due to this recent dryness, is seeing D1 to D2 drought, but much less. The last year at this time there was huge swaths of red on this map, especially in Washington, that we're not seeing anymore. So that's good. And this plot shows the percent of normal precipitation needed to end drought conditions in 6 months. And the color bar isn't the best, but I can interpret for you that we, in this rainy season, will need 110 to 120% of normal precipitation generally across most of these areas in Washington. And the areas with a little bit higher drought categories in southern Oregon and Idaho would need 130 to 150% of normal precipitation over the next 6 months. So it's not as much, it's not a huge amount relative to normal that would be needed to erase the drought in Oregon or in Washington and northern Idaho, but more the farther south you go. Moving on to some impacts. Reservoir levels, considering how dry it's been, you might have expected reservoirs in Washington state to be, and I'm focusing kind of on Western Washington here, both because that's the area I know the best and because that's where it's been driest relative to normal this fall. And city of Seattle is running a little bit below normal in October, but far above what they consider to be low reservoir conditions. And the Yakima Basin is actually running above average and even above last year. So, and that's just a result of the spring being a high snowpack year, and especially in what we had very high snowpack in late season spring. So it's good that that's kind of held over. If it was like 2014-15, for instance, or some of the El Nino springs followed by a warm summer, we might be talking a different story. I think it has started to rain a little bit in the last week, but which has made us feel a little bit better, but stream flow is still running extremely low in Western Washington. The Hoh River out on the Olympic Peninsula is record low right now, only 5% of normal. You can see the median is up around 2,000 cubic feet per second, and 100 or 150 or so is where it's at right now. Middle Fork, Snoqualmie, same story. I think 1988 was lower, but pretty close to record lows there, 10% of normal. But interestingly, late summer, that year that I was mentioning, 2014-15, and especially summer 2015, the Middle Fork Snoqualmie was much lower that year. So it could be worse again. There was enough snowpack to kind of keep at least some stream flow going. Wildfire season is essentially over, I'll say. There's been limited spread still being reported in some of the Southern Oregon fires. And the Bolt Creek fire here pictured in the Washington Cascades has been a big one in this part. And there is now we kind of move on to landslide risk along the burn scar. So, but the fire spread is essentially over. So that's one positive. And there have been a lot of public health impacts from the smoke, I'll point out, even though I think in terms of burn acreage, it was not that severe of a wildfire season as a whole, but proximity to populated areas especially in Washington, the Seattle area had 13 days of air quality of unhealthy for sensitive groups or worse, which was the highest out of even any years that people may remember as being worse smoke years. And a number of these really bad days came just last week. So to summarize, it's warm and dry for most of the summer and early fall. The delayed start to rainy season has made the anomalies even worse in the past 30 days than earlier in the summer. And year-to-date precipitation, though, is still looking good thanks to the wet conditions in winter and spring. And I'm sure the outlook will be better as well. And drought conditions are better as a whole than this time last year, but the stream flows are one of those indicators that just shows how dry it's been, and wildfires are no longer a risk. So that's all I've got. Thank you.
Thank you for that presentation. Next, we have John Gottschalk, who will be talking about seasonal conditions and the climate outlook.
Okay, thank you. Good morning or afternoon. I'm John Gottschalk at the Climate Prediction Center. I'm chief of the Operation Prediction Branch, and I'll provide an overview of some of the latest climate conditions with respect to ENSO as well as CPC outlooks for ENSO, temperature, precipitation, and drought. So first, just a quick review of where we're at currently. We continue to be in a La Nina advisory, focusing on the figure on the upper left. This is the average ocean sea surface temperature departures from normal across the Pacific Basin, and you can see continuation of below normal temperatures from just west of the date line to the South American coast. This has been ongoing somewhat unusually throughout the entire summer and autumn. Also warmer ocean surface temperatures across parts of the North Pacific and North Atlantic. Slide is ocean temperatures, a cross section along the equator with depth. From August 20th, this is the anomaly over the last 5 days. And just wanted to note this, we have continued to see a pretty good reservoir of below normal ocean temperatures at a pretty good depth across much of the East Central Pacific and Eastern Pacific to allow a continuation of fuel, if you will, for the continuation of this La Nina event into and through the winter. The official forecast for the ENSO phase La Nina is shown here with the blue bars for La Nina, gray bars for ENSO neutral, and red for El Nino. And as noted earlier, we expect La Nina is favored to continue through the winter months, the favored category for March season, with the odds for La Nina decreasing gradually, as you can see, over the late autumn into the winter. Where at that point, late winter and spring, we see the gray bars increasing in percent chance. And so from that point on, from the February, March, April period, we're favoring ENSO neutral conditions, pretty high probabilities by the spring. And it is interesting to note a little bit, the El Nino probabilities by the May, June, July period are just under the 30%, which is actually the highest we've seen in a while on the official forecast, although still low. One thing I want to show, I think most folks know just how difficult the wintertime precipitation forecast is, often on the seasonal timescale along the West Coast and overall, and Pacific Northwest as well. During La Nina events, I wanted to kind of show a number of events, which is shown on the left. I know these are small, but just wanted to kind of indicate whether you have a strong or moderate La Nina. The variation is quite large. If you look closely with these plots, you can have, as I think many of you know, very wet winters in the Pacific Northwest and Northern Rockies, quite dry winters in the Pacific Northwest and Northern Rockies, and then same can be said in general for much of the West Coast, across California, Central and Northern California, especially during La Nina events. And so there's quite a bit of variability during all of the different La Nina events, whether you have a moderate or a strong event, and even weak events as well. So that's something to keep in mind. Also, with respect to snowfall, the plot on the bottom right here, this is for the whole period from October through April, and so it's just the average snowfall departures from normal for all La Nina years. So you need to take that with a grain of salt, meaning weak, moderate, and also strong La Nina years. But in general, the signal with generally colder conditions for the most part observed, as well as for the general tendency for wetter conditions in the Northern Rockies and the far Pacific Northwest, that generally has an increased signal for increased or above average snowfall in Washington, Oregon, and Idaho and Western Montana, as well as parts of Southern Canada. With respect to the latest drought conditions, Joe already talked about the U.S. Drought Monitor. The only thing I'll add on with this slide then is that the North American Drought Monitor, which combines Canada, the U.S., and Mexico, the latest one for folks in Southern Canada, drought conditions generally similar to what Joe described across much of the Pacific Northwest region, areas of D1 in some areas, and then a little bit further to the east, potentially extreme drought there north of Montana. But again, this is from September 30th conditions, so this is only updated once a month as opposed to weekly. So the next update will be sometime in early to mid-November through conditions through October 31st. What I do want to show also is some of the short-term forecasts before going into the longer-term winter, because we've had a we're undergoing a pretty strong pattern change from what Joe had been describing quite a bit with respect to the last several months. We do this. What's shown here on the left is the days 8 to 14 upper level pattern, which tends to which is, the forecast is for more in the way of upper level low pressure and flow off the Pacific storminess during the period. This actually will start prior to this period in the week 1 period. And generally with the week 2 temperature precipitation forecast on the right, we continue, not surprisingly, favoring above normal precipitation, which is very good news for much of the northern tier of the country, especially the Pacific Northwest, parts of the northern Rockies in the 6 to 10 day period, which is not shown here, and also during the days 8 through 14, which takes us through the November 6th period. Another thing I want to show, this will be updated later today as well, but the early part of November at higher elevations, risk for potentially heavy snow and high winds along the coastal areas. This is from the days 8 through 14 U.S. hazards outlook. And so it's not just the total precipitation forecast that I showed previously, but also just general stormy conditions that are typical as we enter the storm season in the Pacific Northwest over the next couple of weeks. Moving a little further out into November, our week 3 and 4 outlooks for temperature and precipitation, similar graphics for what was shown on the previous 2 slides ago. But in general, we're still favoring a pretty good jet across the Pacific and troughing just to the off of the west coast of North America. And so I just wanted to focus on the precipitation outlook during this period. Although the uncertainty and predictability decreases as you go into the week 3 and 4 period, we are at the current time favoring above normal precipitation, which again is good news for much of the region moving forward into the middle part of November. Now, taking to the longer ranges, what we expect for the seasonal outlook for November, December, and January, and then I'll show December, January, February next. Temperature on the left, precipitation on the right. Warm shades favoring above normal temperatures, blue below normal, and green and brown respectively for above and below normal precipitation on the right. Generally, for the November and December, January period as a whole, we feel that generally warmer conditions are going to dominate from much of the early part of the period. It tends to be a colder signal that comes in later. And so for much of the Pacific Northwest, we have equal chances of the 3 categories with a slight tilt towards above normal temperatures across parts of southern Oregon, southern Idaho, and so on, with precipitation expected or favored to be above normal, especially across the northern Rockies and parts of the Pacific Northwest. This is consistent with dynamical model guidance and, of course, La Niña based composites and typical impacts. Again, there's quite a bit of variability during La Niña events, which is why there's a large area of equal chances along the West Coast. It can be quite challenging where this dividing line will be each year. As we move into the December, January, February period, as I mentioned, we do expect cooler conditions to dominate. November times off and February becomes part of the 3-month seasonal average, favoring below normal temperatures for basically the northern half of the Pacific Northwest and northern Rockies, extending eastward to the western Great Lakes, and warmer conditions or above normal temperatures favored to the south across parts of the central Great Basin and Southwest. We do think above normal precipitation remains favored for December, January, and February across pretty much the entire Pacific Northwest, Northern Rockies region. In general, the signal in that area is typically strongest in November and December into January, and then shifts a little further east towards the Northern Rockies and High Plains later on. But that's the official forecast for the winter itself. And with that as background, the latest U.S. seasonal drought outlook shown on the left, and not surprising, with respect to their rainy season and then normal climatological precipitation increases, plus the favoring of above normal precipitation associated with La Niña areas in green, in gray and green, indicating expectations by the end of January 2023 to be improved or removed. Hopefully that comes to pass. And this is associated with the short and extended and sub-regional range precipitation improvements that we are tending to favor right now, as I showed through mid-November. Also, the La Niña base state or conditions that we typically have in the region, as well as pretty consistent guidance from short-term climate prediction models through the winter season also, which I haven't shown those today. So the take-home messages is that La Niña conditions continue in the Pacific, as shown by both the oceanic and atmospheric conditions. Didn't show the atmospheric conditions, but they were very consistent with ongoing La Niña. La Niña is expected to most likely remain in place through the winter months and linger into impact-wise into the early spring, at least. Above normal precipitation is most likely for the Pacific Northwest during the November, December, January, and December, January, February 3-month seasons. Odds decrease thereafter for western areas. Below normal temperatures are favored for the northern half of the region, mainly later on December, January, and February, and January, February, March, as colder conditions are typically are more likely a little bit later in the winter. And as I mentioned, the shorter term guidance and forecast from CPC indicate a favorable pattern for improvement in drought conditions across much of the region over the next 1 to 3 weeks. And it's important to note as we go through the winter season to monitor some of CPC's shorter-term outlooks, week 2, week 3 and 4, monthly, and so on, as there are expected to be quite a bit of variability within the season. And these outlooks can provide some additional lead time during the winter as a whole for any pattern changes with respect to more storminess or less. Thank you very much for your time and attention. I'll turn it back over. Thank you.
Great, thank you, John. I'm going to step in as we transition to our next speaker and ask one question that either John or Joe can take on, and that is, what is the highest temporal resolution for drought monitoring systems? I see monthly and weekly mentioned in these presentations. Are there any indicators that are available at a daily scale or higher temporal resolution? Can either of you maybe address some of the other indicators that are out there that are of higher temporal resolution?
Joe, would you be able to answer that? If you're on.
Okay, and if not, we can follow up with the person asking the question.
Yeah, I think I would like to follow up with that. We have a number of folks here at CPC that would probably be able to answer that question better than I.
Okay, great. I am going to share the next presentation. Give me one moment.
In the meantime, I will introduce the next speaker. Next, we will hear from Megan Collins, Brett Hatchett, and Keith Jennings, who will be discussing how citizen scientists help advance precipitation phase research.
No, and thanks, Britt. And thank you to everyone who is here. We are really glad to be sharing mountain rain or snow with you. We're going to do 3 things today. We're going to talk about what mountain rain or snow is and how we involve community observers for science. We'll talk about what we've learned so far in the project. And then if the topic of this work, which is the rain-snow transition, is of interest to you, I'll put out an invitation to carry on the conversation to brainstorm ways to bring this to your region. As Janelle mentioned, I'm Megan Collins. I'm with the Desert Research Institute. I'm here with my colleagues Keith Jennings and Ben Hatchett. Keith is a hydrologist, Ben is a hydroclimatologist, and my background is science communication. The goal of mountain rain or snow, oh, thank you for that. The goal of mountain rain or snow is to improve precipitation phase estimates near freezing. If you are already familiar with why this is challenging, then you know that there's a lot of uncertainty in the rain-snow transition just below freezing, above, up to a few degrees above freezing. If you are not familiar with why this is a challenge, you may be inherently familiar with the phenomenon. You can see in this photo that there's snow can fall above freezing. It's not a change in the law of physics, but it's simply a factor of weather, and we often see it in our mountain regions. Next slide, please. So the goal of mountain rain or snow is to better monitor and estimate precipitation phase over a diverse range of US hydroclimates. This project is funded by NASA, and we aim to help improve NASA products, including output from the Global Precipitation Measurement Mission. The reason that we use community observers is because ground-based observations are really the best way to differentiate between rain, snow, and mixed precipitation. We have a range of technologies that help us do this, but we currently, really the absolute best way to get these estimates or get these observations is real people. And so we've built a network of over 1,000 observers who send us observations in real time. I'll explain how that works in a second. And this is all with the goal of helping to improve the technologies behind our rain snow transition estimates. So I mentioned earlier that one of the things that we'd be doing today, thank you, is to share with you what we've learned so far. And so this is a heat map that Keith put together that shares where our observations have been submitted last season. So from November 2021 to May 2022, we had over 15,000 reports of rain, snow, and mixed precipitation. Here you can see anywhere there's non-gray color is where we've received reports. The yellow and orange indicate higher numbers of reports, and purple indicate kind of in the medium range. And expanding data collection in each region can help us get a locally specific analysis. And I'm going to talk about two analyses that Keith has done for that. Next slide, please. Before I jump into the data, just a quick top line summary. So plant the seed. We all know that a threshold of 0 degrees Celsius for the rain to snow transition isn't really accurate all of the time. But what is interesting and what this project is finding is that the nature of that transition differs by region. Also, because we are focused on improving the ability of technology, specifically satellites, to improve these, our satellite technologies also struggle in different ways in different regions to estimate the rain snow transition. Next slide, please. If you need a refresher on snowfall probability curves, which is what I'm going to talk about in a second, I'd like you to imagine that you're playing skee ball for the first time. If you're playing skee ball for the first time and you want to know the probability of hitting a 50 versus a 20 point area, you might do a number of random throws, plot your scores. And if you click once, you can see that if you did a number of throws, you might throw 3 balls in the 10 zone, 2 in the 30 zone, and if you're lucky, 1 in the 50 zone. You might put your scores on the x-axis and you might put probability on the y-axis, and you could come up with essentially a probability density plot through which you could fit a line. And that's essentially what we've done with our community observations to develop snowfall probability curves. Next slide, please. So our 2021-2022 data allowed us to create snowfall probability curves for 7 ecoregions. You can see that there's air temperature plotted on the x-axis and probability of snowfall plotted on the y-axis. And what I'd like to just bring your attention to is that the steepness of the curve is not consistent across regions, and the place where the curve crosses 0, so the snowfall probability at 0 degrees Celsius is not the same across regions. So that's one thing you can bring your attention to. Keith, do you want to add anything in terms of snowfall probability curves here?
No, let's just keep going through. Ask any questions if we got them at the end.
Sounds great. So on our next slide, you're going to see a comparison between 3 of those regions. So we've plotted the Southern Rockies, the Sierra Nevada, and the Northeast Highlands. And what this plot shows, interestingly, is that in our Western ecoregions, we saw mostly snow near 0 degrees Celsius. The transition from rain to snow, so that 50% probability threshold, took place at different temperatures in different areas. So in the Southern Rockies, that threshold was pretty high, 4.6 degrees Celsius. But in the Sierra, we're looking at a 2.1 degrees Celsius threshold, and then the Northeast Highlands is much lower at 0.7 degrees Celsius. So this plot not only shows differences between regions, but it's also shows the kind of unique value that this project can bring. With ground-based observations from community members across a landscape, we can build these curves and better understand the nuances between locations. Next slide, please. I also let you know earlier that we would be looking at success rate of one of the NASA satellites. I said that satellites struggle in different ways in different regions. So this is an assessment of the accuracy of the predictions of one of the NASA GPM satellite missions. So I'll first draw your attention to the color bar. Darker colors indicate lower probability or lower success rate, and lighter colors indicate higher success rate. So if we compare the mountain rain or snow observer snowfall probability curves, or excuse me, if we compare mountain rain or snow observers input with the IMERG precipitation phase predictions, we can see that satellites struggle in different ways in different areas. So if you click once, you'll see that in the Southern Rockies, too much snow was predicted at those higher temperatures. You click again. In the Sierra Nevada, too much rain was predicted. And finally, not enough freezing rain or mixed precip was predicted in the Northeastern Highlands. So by continuing to build our large database of these observations, we can ultimately look for improvements in these technologies. So how do we do all this? Next slide. Well, I mentioned that we have a large network of community observers. We engage those observers via text message, and we have regionally specific text message groups or text message communities that to which we send alerts. And so if you wanted to get started, you could find the keyword in the right-hand column that corresponds to your region, text that keyword to our number, and we would send you a link to our browser-based app. And our browser-based app functions through the browser in your phone, and that is how we receive observations from all of our observers. Next slide, please. The browser-based app looks like this. It's a really simple interface, enables people to sign in, send their observation of rain, snow, and mixed, and see past reports and update their profile. Next slide. We send alerts because it is a really effective way of continuing to mobilize our observers in near real time. And if you click once, you can see a plot of the time since last notification. And you can see that there are a large density of bubbles down there in the lower left. That's because generally less than 1 day goes by after an alert where people send us an observation. Up at the top in the speech bubble, you can see an example of what an alert might look like. We send alerts when there's a storm approaching of interest. So next slide, bottom line summary is that mountain rain or snow uses ground-based observations of winter weather submitted by community observers to improve estimates of rain, snow, and mixed precipitation. I welcome you to reach out if you would like to bring this program to your region. So if you'd like to add another regional keyword to our list, or if you are located in Oregon and you want to help expand so we can improve the data in your local area, please reach out. Next slide. My contact information is here. You can text the project, you can email me, and you can check out our website if you want more information. It's rainorSnow.org. With that, I conclude.
Thank you, Megan. And last, we'll hear from Ben Hatchett, who is going to be talking about monitoring the daily evolution and extent of snow drought.
And apologies, Ben, I'm looking for you on my list here. Give me.
Okay, cool. Yeah, I was like, I don't see a thing to click.
let me see if I can do it this way. For some reason, you're not appearing, but here we go.
Ah, cool. Cool. Well, thank you for the invitation to present. So I'm Ben Hatchett, and I've been working with Dan McAvoy, also at the Desert Research Institute, and Alan Rhodes at the Lawrence Berkeley National Lab on some varied snow drought topics. And one thing we've been working a lot on is how to measure and monitor snow drought at daily timescales throughout the Western US. And in the West, we know we have booms or busts in terms of snow. Left-hand side shows a view from space. This is NASA's MODIS imagery. Excellent year. We have happy M&Ms when this happens. And on the right-hand side, we have our characteristic snow drought year when we have less snow than expected, or to kind of extend Kelly Redmond's, drought is not enough water to meet one's needs. Snow drought is not enough snow to meet one's water resource objectives and ecological goals as well. And as a result, we end up with a sad set of M&Ms. And so our Western US supply and demand connections, I think it's just nice to kind of always revisit the fact that our sources of much of our water in the Western US doesn't coincide with where we need that water the most. And so our mountain-derived snowpack, our sources of water, and how we store it and move it throughout the West and where we need it the most really varies, and they're oftentimes disconnected. And so especially in terms of where that demand is in the Pacific Northwest, you can see on the right-hand side, big needs in terms of some irrigated agriculture in a few locations, but really the hydropower needs, to me, really stand out, as well as the supplies for public water use, as well as ecological uses. And throughout all of this, we have a huge reliance on snow. So we need to know how much snow do we have, how is that evolving with time? And that's kind of the motivation for development of this sort of near real-time snow drought tracking that we've been working on. So much of what I'll talk about today is highlighted in this paper that came out earlier this year in Natural Hazards and Earth System Science. Happy to send you a link if you have trouble finding it, but basically if you just Google the title of this talk, this will take you to the page where a lot of what I'm showing is going to be found and described in additional detail. So our motivation from this, some of you may have heard of the Madden-Julian oscillation, an intraseasonal mode of tropical Western Pacific and Eastern Indian Ocean variability in the location of tropical convection. Our real breakthrough was with monitoring snow drought came from MJO phase diagrams, how we measure and can forecast where and observe where something has come from and where it's going in terms of a couple different variables. And I really like these kinds of graphics because they tell us where we've come from and perhaps where we're going if we include forecasts. And it allows us to annotate them and explain both the processes driving these changes as well as their impacts. And so we've been trying to incorporate this into what we call the snow drought phase diagrams. And so this phase diagram concept essentially takes the daily observations of snow throughout the year. Here we mostly use SNOWTEL observations, which are at daily timescales, but we can also use gridded products, as we'll show later. And we basically plot the water year accumulated precipitation, where we calculate that accumulation as a percentile based upon the period of record, and our instantaneous snow water equivalent also as a percentile, and we plot it throughout the course of the year using different colors to help us find where we are in the year. So the colors on these plots correspond to the different months, and then there's little first of the month letters to help you sort of orientate if you're having a hard time. And so we can see from October through the course of the year, there's a lot of variability that goes on in terms of our precipitation and snow conditions. And essentially where we think about snow drought is where we start to get below that median snow water equivalent and start to get deep into snow drought or the start of snow drought, I suppose, at the 30th percentile. Once we're at less than the 30th percentile, that's where we start getting really concerned about much below expectations in terms of snow water equivalent. On the bottom there's the precipitation axis on the x-axis. The further to the left we are, the drier conditions are compared to what we expect. The further to the right, the wetter conditions are relative to what we expect for a given point in the year. And so we can follow these lines, and then we can annotate them and kind of explain what's happening as a way to help communicate when did we go into snow drought and why might we have gone into snow drought and what kinds of other things happen that may have helped us out here in terms of snow drought amelioration. And there's many different potential interpretations of these trajectories. A few examples are shown on the right-hand side there, how we kind of move around. Happy to entertain new ideas or reinterpretations of this. It's all very much flexible, and we're interested in kind of thinking about how we move around on this curve. And so why are we using percentiles instead of percents of average? Well, there's a lot of variability in our snowpack, and below is an example from the Wasatch in Utah. 60% of median in the Wasatch or a lot of the higher mountains of the northern tier of the United States is a lot different than 60% of average in, say, Arizona or California. And I don't really know what 60% of average means, but I definitely know what the bottom 15th or 5th percentile means. So it really helps compare across locations, even within a basin, if you have multiple stations in basins or broader, more west-wide. We also like this percentile approach because it helps us connect with US Drought Monitor categories. We use the same percentile-based categories there as a way to help link to US Drought Monitor activities. And currently, we're using the complete data set to calculate these. So we're not sensitive to changes as we shift every 10 years into new climate averaging periods. However, we may want to stick with kind of a more historical period as we continue to shift towards a more snow-free future, so that we don't really bias our results towards this decrease in snow that we're continuing to see throughout the West. We want to stick with where we kind of what we expect and what we built our system on. And so for time, I won't go too deep into this here, but essentially the Wasatch was in snow drought. I wouldn't have noticed if I had looked at percent of median, but we were actually in some of the lower snow percentiles there, and there was a big avalanche incident that resulted partly due to persistent weak layer formations and characteristically shallow snowpacks that resulted from dry conditions. Subsequently, stormy conditions led to loading of that snowpack and a bad outcome there. So it's kind of another application of snow drought to recreation. So let's look at a couple examples we're going to look at Washington here. 2015, our quintessential snow drought in the Pacific Northwest, I think, really where we kicked off this whole concept of, whoa, we got a bunch of precip, but we didn't have a lot of snow. That's kind of interesting. What's going on there? And for two different locations, Spencer Meadow on the left-hand side, a little bit higher up at Green Lake on the right-hand side, you can see that we're in that fourth quadrant, that bottom right-hand quadrant for much of the year. So we are above normal in terms of precipitation accumulation, but well below expectation in terms of snow water equivalent. And as the winter progressed into spring, you can see a leftward shift because there was actually some drier than normal conditions that took place. So we did not have a snowpack, and that there was almost no snowpack recovery. But because conditions dried out, we started to shift to the left. And if we just took the April 1 snow water equivalent, for example, at Spencer Meadow on the left, where that A is, you'd see that we'd be in the dry snow drought category because we are a little bit below normal in terms of precipitation, well below normal in terms of snow water equivalent. But that hides the fact that much of the year we actually had a lot of above normal precipitation. And so there could be some hydrologic impacts that we may reinterpret as a result of looking at this way. 2001, nice example of classic dry conditions. Far on the left-hand side, you can see we're well deep into the low percentiles in terms of both precipitation and snow water equivalent. And this is what we term the dry type of snow drought, below normal snow, much below normal precipitation. So this goal in linking to hydrologic implications, example of warm versus dry, 2001 versus 2015 again. Now we're looking at Paradise on the southern flank of Mount Rainier. And as we think about this, I think it's important to consider, things like in terms of runoff, the timing of the flows, the magnitudes of the flows, the water temperature with respect to fisheries, as well as impacts considerations. How do we store water? How flexible is management? And an interesting thing, if we look at cumulative discharge at the Nisqually River, is in 2015, there was a greater total amount of water compared to 2001, but much of that water came out much earlier and much earlier than normal, whereas 2001, there was a lower total amount of water, but it came out later in the year, and you can actually see the slope of that line is a little steeper later in the year, reflective of having a little bit more snow that came out, and it was a little bit cooler, so it came out longer. So some of the late season stream flow implications and water temperature implications could be, you could kind of think about those in context of when did the water come out and what kinds of precipitation and snowpack regimes were we undergoing. So we're looking into adding an operational spatial component to this. This is an example from the paper, again, that 2015 year. You can see January and February at the top there, those green colors, snow drought, but on the warm type, above average precip, much of the West in the dry type. As we progressed later into the year, we got all into the dry type. So sad M&Ms throughout the West, throughout much of 2015. And something else we're working on is trying to link some of these extreme events to circulation anomalies, as well as to solar radiation, temperature, precipitation anomalies, to try to get a better handle on how can we forecast these changes, either going deeper into drought or drought amelioration as our skill in subseasonal and seasonal forecasts improves. We're also kind of scaling this up to just looking at the entire West in terms of snow drought type, how that varies for different times of year that may be of importance, and what kinds of trends we're seeing, as well as variability. So we have a tool that's still in progress. It does work, but you're welcome to go to this website and break it. When you go to the site, you will need to form a login. It'll make it look like it's not going to work. Get a login, sign up, get in there and play with it. Some examples of what it looks like down below are shown. It can make snow drought phase diagrams. It can give you daily SWE time series from the SNOTEL network. And so we're very interested in your feedback with this tool. So to kind of wrap this up, I think it's a good technique using stations and basins and regions to really think about where our snow is, how it's evolving through time, and how it ties into all of these critical components of our Western infrastructure and really our way of life in the West. It's all connected. And that's something to just closing thought here to think about as we move into a warmer future is when are we going to hit these persistent, when is what we call low to no snow, persistent snow drought going to take place? And there's some nice work that Erica Cirillo-Woodburn and Alan Rhodes have been leading to really highlight when we expect snow drought to become persistent every year. And that's going to probably occur around the mid 21st century, 2055 or so. And we have a warming level to try and avoid at about 2.3 degrees C. So I'll stop there. Thank you very much for your time, and happy to entertain any questions.
Great, thank you so much. We had one question that I think was answered maybe in Megan's last couple slides, but an interest in a Pacific Northwest region or Central Washington for the citizen science monitoring. And so I did put Megan's contact information in the chat box. But Megan, did you want to say anything about adding regions?
Briefly, we would love to chat more. So please reach out. I don't know, I can't see everyone's comments, so I don't know who said the comment, but please reach out. I would love to talk more about expanding into your area.
Great, and I'll make sure you guys are linked up after the webinar. John, if you're still on, there was one other question, just kind of asking generally how the drought outlooks are put together. In the last couple minutes, would you mind maybe a summary of how the drought outlook comes together?
Sure. Just want to make sure everyone can hear me. The seasonal drought outlook, it could basically, it's a combination of where we're at antecedent condition wise, what the expectations are, just as far as the seasonal cycle for precipitation, meaning the changes in climatology as a baseline in general. And then there's a number of different forecast tools or information that the seasonal drought outlook forecaster has available to them. It's in addition to just the regular seasonal precipitation and temperature outlooks that are official outlooks, there's a host of, as I mentioned briefly prior, short-range climate prediction models and simulations that go out a number of months. And those are also used to help augment the forecast based on ENSO and during ENSO neutral years where we have not much information from that perspective. We have to rely on more the dynamical model predictions as well as some other statistical and empirical tools. But I will say that short-term forecasts do play a role in the drought since it's an integrated quantity because you'll notice that short-term precipitation accumulation, for example, or snow in general, in the shorter term, meaning in the next few weeks, as I was showing in some of my plots, also are included, whereas for the seasonal temperature and precipitation outlooks, the verification period starts at the beginning of the following month. So it's a combination of a number of integrated precipitation forecasts from both statistical and dynamical model predictions, as well as climatology, and in addition to where you're starting from with respect to antecedent conditions. So I hope that helps some.
Great. Thank you so much. And I think that we've been brought to the top of the hour. Thank you to our speakers and to all our attendees. And there's a couple things we'll follow up, connecting some attendees with our speakers post-webinar. And we look forward to seeing you in December. That webinar will be a little bit earlier than normal due to the holidays. And I'm just triple checking that is December 19th. So we look forward to seeing you all then. Thank you so much.